Hi guys, in today's video we are going to continue our discussion about multiprocessor architecture. Just for a quick recap, during the previous video we have studied about multiprocessor architectures, then the use of multi-level caches, which actually resulted in two problems. One is cache coherence, and as an immediate consequence, consistency problem. Just for some quick recap, just go back to the previous day's discussion. Yes, if you can recall the previous day's discussion, you can find that in multiprocessor centralized shared memory architecture, you had a number of processors. Then you have a centralized shared memory which can be used by different processors through interconnection network. However, all the processors had their native caches attached to them, which actually resulted in cache coherence problem. And the cache coherence problem actually was something like this. Say you have two processors in your multiprocessor architecture, processor P1 and processor P2, and in your centralized shared memory, there is a data item X. Now, at time t, what happened? Processor P1 made a request for this item X, which eventually was brought into the native cache of processor P1. At the next time cycle, that means at time cycle T2, processor P2 made a request for the same data item. So this data item X from centralized shared memory brought into cache, which is native to processor P2. Then at time slot T3, that means at the next time slot, what followed? This data item was updated by processor P1. That means X was now changed to X1. And if your update policy is memory update policy means memory update policy is write through, then into the centralized share memory, this item has been replaced. However, after this time, if processor P2 makes a request for this data item at that location, it will not have access to the latest value, which is x1 now. Why? Because now there will be no cache miss. That means processor P2 will be able to find the data item at that particular memory location into its cache itself. However, if you carefully follow the situation, processor P2 doesn't have access to the latest value. It has access to some old value. And this results in a peculiar problem. That means there is some kind of inconsistency among the data which is residing into the centralized shared memory and the data inside the cache. This problem is cache coherence. You can see that different caches are holding the inconsistent value of data within themselves. So this was in brief the cache coherence problem and consistency which arises due to this. Now in today's video we are going to see how to solve this problem. But just before looking into the solution, have a look at the definitions of cache coherence and consistency. Cache coherence means a memory system is coherent if any read of a data item returns the most recently written value of that data item. That means if you go back to our previous example, our memory system in that example would have been coherent if processor P2 had access to the most recently written value of that data. That means x1. However, in that example, processor P2 did not have access to the most recently written value of x. So there was a cache coherence problem. Then come to consistency. This indicates when a modification to memory is seen by other processors. That is, will be returned by read. So memory needs to be seen by different processors. Modification to memory. Memory location at X has been updated by processor P1, if you can recall, and it was changed to X1. However, this modification was not seen by processor P2. So, in that example, the memory system was inconsistent. And our goal in this video is to learn about the methodologies by using which these problems can be solved. So, to solve this situation, you have basically two protocols. One is Snoopy Bus Protocol. That means the sharing status will be distributed and kept with the block in each cache. The caches are usually on a shared memory bus. The cache controller snoop the bus to watch for transactions that occur on data block they hold. I believe that when I read this definition now, it have not made any sense to you. If you look into the examples that I'm going to discuss later on, this definition will be more clear to you. Just for now, look into the definitions. Then come to directory-based protocol. Here, sharing status of block of physical memory is kept in one location. At first, let we have a look at this snooping protocol. So here is it, snooping bus protocol. It essentially involves two things. One is write invalidate and another one is write broadcast or write update. So how they go? In write invalidate, what happens? The basic idea behind this protocol is that it writes to a location and invalidates other caches copies of the same block. right? Just have a look into the example. Then this statement will be clear. First, say in your multiprocessor architecture, you have two CPUs. One is CPU A and another one is CPU B, right? Then say CPU 1 for the time being makes a request for the item which is residing at memory location X. Essentially, here there will be a compulsory catch miss. Why? If you can recall memory hierarchy module, there were three types of catch misses. One was compulsory, that means when the entire processing starts, then you had capacity, then you had conflict. Here you will have compulsory catch miss. So contents of the memory location X will be brought into cache, which is native to CPU A, right? Say 0 is there as a next time instance. The situation follows like CPU B makes a request for the same memory item. Again, there will be catch miss and the contents of memory location X will be brought into CPU B. So now into your centralized shared memory location X, you have 0 for all the two cases. In your cache of CPU A, the location of content X is brought, as well as in cache of CPU B, you have the same item. You can see that in all the three locations, you have zeros, right? Now, what happens? Say, as a next time instance, CPU A modifies the content into its cache. Have you got my point? It goes like CPU-A changed the value of the content inside the cache from 0 to 1. You can see it here, right? At the same time, if your memory writing policy is write back until this memory block gets replaced by some other memory block, the contents of the centralized shared memory location will not be updated. So you have inconsistent pair of data. In your cache of CPU-A, you have 1, but in your centralized memory location X, you have 0, as well as at the same time, you have 0 into the cache of CPU-B for the same data item. Cache coherence problem is here, as well as memory inconsistency is here. So how to solve this? Just do one thing. Just send a memory invalidate message through your shared bus. Shared bus means the channel through which different processors and different memories communicate with one another. Just send one write invalidate message through the shared bus, and this write invalidate message will be captured by the caches and memory locations where there is a copy for the data item which is residing at X. So once those memory locations get this write invalidate message, what they will do? They will invalidate the data which is with them. So If you follow this example, our example, CPU-A updates the data item residing in its cache, and at the same time it sends one write invalidate message to the shared bus. So for the same data item, there is a copy into cache of CPU-B and there is a copy into the centralized shared memory location X. And once they grab this write invalidate message, what they will do, they will invalidate their content. I for invalidate. So this was the goal of write invalidate message. So now you get the justification of the basic idea behind this write invalidate protocol. It writes the location and invalidate other caches copies of the block. It did. Now at the next stage, what will happen? It will send a write update or write broadcast message to the shared bus. And the goal is to update all cached copies of the data item when it is written. So how this goes on? This goes on like after write invalidate, this cache, that means the cache which is native to CPU-A has the updated value and other cache, that means cache to CPU-B has been invalidated. So if you want to provide it with the updated value, now CPU-A will send a write update message to the centralized shared bus with the updated value, and it will again be cached by the CPU B, and the cached copy of it will be updated with the new value. How it goes on? If you follow the course, here the copy has been invalidated and here the broadcast happens by CPU-A with the new data item for new data value for X. So now CPU-B gets the broadcast message, and in this broadcast message, this new value for the data item X has been embedded. So what CPU-B does, it updates its cached copy with the new data item. So now you can see that there is no inconsistency problem, there is no cache coherence problem. All the caches have access to the latest data value, and if you follow the definition of inconsistency, where is it? Where is it? Just bring it down. Yes, here is it. Modification to memory is seen by other processors. That means here you have been able to solve the inconsistency problem also. How? The memory modification by processor A is now visible by all the processors. So inconsistency problem in this way has also been solved. So here is the diagrammatic representation of the same concept. Here you have three processors processor 1, processor 2, and processor 3. And into your centralized shared memory, you have X. Now, this X in some time, at some point of times, has been accessed by different processors. So this X has been cached by all the processors. You can see that this X is residing into the corresponding cache memories. Now, what happens in course of time is processor P1 does what? It updates the data item to X1. And if the update policy, memory update policy is right through, when this update happens, then into the shared memory, this value is updated at the same time. But now there is no cache coherence problem. Why? Because while processor P1 was updating the value of X to X1, it send a write invalidate message to the shared bus. WI stands for write invalidate. So this write invalidate message was captured by processor P2 and processor P3. So what they have done, they had invalidated the data items which was with them. So now you can see that the X which was residing with the caches of processor P2 and processor P3 has been invalidated by this I. And at the next time, what goes on? At the next time, after invalidated message has been acknowledged, this processor P1 sends a write update or write broadcast message to the shared bus, and again this write broadcast message is captured by two other processors, and their cached values has been updated with the new value. Now just think of the problem which might arise due to this Snoopy bus protocol in terms of bandwidth requirement in this shared bus or in your interconnection network. Just pause the video here and think about it. So if you can observe carefully, you can find that there will be frequent bus activity occur in this protocol. That's why bandwidth requirement will be much higher with this Snoopy bus protocol. To compensate the bandwidth requirement, another protocol has been proposed, which is directory-based protocol. Just look at the statement, and here is the justification behind using this directory-based protocol over the Snoopy bus protocol. By using a multi-stage network for building a large multiprocessor with hundreds of processors. Now, the assumption is that, say, you don't have three or four processors in your multiprocessor architecture. Rather, you have hundreds, thousands of processors in your multiprocessor architecture. The Snoopy Catch protocol need to be modified to suit the network capabilities. If you have hundreds of processors in your multiprocessor architecture, then this broadcasting task becomes costly. How? Because whenever you broadcast some message, it needs to be reached to hundreds of another processors. So it becomes very expensive to perform in a multi-stage network. The consistency commands is sent only to those caches that keep a copy of the block. This is the reason for development of directory-based protocol for network-connected multiprocessors. Why? Because in this scenario, you will see that actually message need not to be sent to different processors. Rather, different processors will check that the data item it is going to access is consistent or not. In other terms, say processor P1 is going to access the data item at memory location X1. Before bringing it to its native cache, it will check that at that particular time if it is being accessed or being modified by some other processor or not. In this way, it will be able to solve the cache coherence and inconsistency problem. At the same time, it will mitigate the higher bandwidth requirement because there is minimal requirement of network access in this case. Just look into this diagram. In this diagram, what happens? You can see that you have three processors in your multiprocessor architecture. Here are your native caches for the different processors, and they are connected something like this. But this is your centralized shared memory. Along with centralized shared memory, you are maintaining a director. Now, what is the process of this directory-based protocol and what is the necessity? Say there is a data item at some location X into your shared memory. Now, at some time instance t, this data item has been required by the process into processor 0. So essentially, this data item will be brought into the cache which is native to processor 0. Now what will happen? This directory will hold the information about the entire happenings that processor 0 is now modifying the data item into memory location X. Now what is the advantage? Say after this time instance, at time instance t plus 1, that means at the next clock cycle, processor P1 makes a request for the same data item into memory location X. But when it will try to access this memory location, this directory will give it the message that, oh brother, you cannot do this thing. Why? Because your fellow neighbor, that means processor P0, is now modifying this data item. So just hold on for the time being. Let him be finished. Once he is done, then you access it. So once processor 0 is done with X data item, this directory will be updated with the new information that processor 0 is done. So now processor P1 will have access to the newly updated data item. In this process, actually what happens? You solve the coherence problem. You see, at the same time, you don't have to depend much on the network bandwidth on network. So these were the two protocols by which this cache coherence and inconsistency problems has been solved. Now, as I always say, first study the reading material, then watch the video, then once again go back to the reading material and read it in between the lines. Whenever you think it is necessary, take notes and keep learning. Thank you.